All right, everybody, welcome back. It's Monday, April 13th, entering into week 12 of the semester. Thanks, everybody, for hanging with us. Homework number 3, I've adjusted the due date on that from today. I know there was a little bit of confusion with people thinking it was due at either noon or at midnight, and I wanted to make sure that we had enough time for everybody. So that is now due tomorrow night at midnight. That's Tuesday, April 14th at midnight now. If you have other stuff that's coming up, maybe you have to do some extra helping at home with family members or whatever it may be. I want to make sure that everybody knows that due dates are my lowest concern right now. I want you guys to do these assignments because they help you to understand the material a little bit better. If that means you need a couple extra days to get it done because of having to be at home and listen to these lectures online, that's totally fine. Please reach out to me. The biggest thing that I want to make sure that all students in the class know is that by reaching out to me, Josh, or anybody associated with the class and saying, hey, I need a lecture time. Hey, I need some help with this. I don't understand this. Or, hey, what resources are out there for me to help me get through this class? That's not bugging me. That's not bugging any of us associated with this class. We're going through an unprecedented kind of change with this class this semester. And our goal as instructors is to make sure that every one of our students gets through the class with the content they need to move on in their careers. And that's our entire goal. It's not to, grade really hard or do anything like that. It's just to make sure that you guys get the content you need. So please don't feel like you're bugging us or, doing whatever by emailing. Send an email. I'm happy to have individual video conferences, phone calls, if those are easier, anything like that to help everybody get through this class. So really keep that in mind as you're going through the class, especially as we get closer to exam number 3 and the final, because those are coming up in a couple of weeks. So let's pick up where we left off with talking about altitude. Last week, when we finished on Friday, we talked about altitude, how it relates to just general population. When we're moving from low altitude to high altitude, what happens to our physiology? How does that change? Today, we're getting into the fun part because we're going to talk about how you can use that physiological adaptations that you get to potentially enhance your athletic performance. You've probably heard about this before. So we're going to get into some of the physiology, and your homework assignment is about that specifically. And then we'll get into a little bit of breathing regulation. So why do we have the breathing frequency and tidal volume that we have? What is happening within our body, specifically within our blood, that is relaying that information to our brain to say, hey, you need to either breathe more or breathe less. Okay, so that's what we'll be getting to eventually. So let's start with a quick little review of where we were. First one we're going to go over, okay, how are we going to determine what are the steps for comparing the partial pressure of oxygen at sea level versus altitude given the information from weather report? Okay, we're going to change it up a little bit from what we did. And I just want to make sure that everybody understands these steps because it's good information to have. So step number 1 is you want to convert from, It's inches of mercury to millimeters of mercury. So we multiply our 29.99 times our conversion factor, which is 25.4 millimeters of Hg per 1 inch. And then number 2, what you would do there is multiply by the partial pressure. Total pressure, which is what you get from this multiplication right here. And you're going to multiply that by the percent of oxygen, okay? And that's going to be in the atmosphere, and that's generally 20, or we'll do 0.2093, which is 20%. Now, that can be manipulated. For example, they have a low altitude chamber over in the High Altitude Performance Center, and what that does is it pumps extra oxygen in there so that this partial pressure of oxygen goes up. The reason it goes up is because the percentage of oxygen in the air goes up. So they put extra oxygen in that chamber. So let's move it, instead of 20%, we'll move it to 30%. Then if we're multiplying 30% by the same atmospheric pressure, guess what? The partial pressure of oxygen is going to go up and your oxygen saturation will go up. Okay, so that's the reason why they do that. Now, if we wanted to convert Laramie's barometric pressure, which is reported from a weather report in this 30.4, remember, that's a corrected value. So we don't want to start with that 30.04. We need to calculate the correction factor. And the general thing that we need to do for that is we take 760. And that's the reason we're using 760 is because that's a kind of classical reference point for the millimeters of mercury in one atmosphere. Okay, so 760, we're going to subtract the altitude of location in feet. We're going to multiply that by 0.026 because remember, we're losing about 26 millimeters of mercury per 1,000 feet. Okay? And then we're going to divide that all by 760. And if we divide that all by 760, that gives us our conversion factor. We multiply our 30.04 times that conversion factor. Once again, pull in our 25.4 up here, and that will give us our total barometric pressure for the location that we're looking for. Practice this one on your own. I'm going to go over the answer to it on Wednesday's lecture. If you have trouble doing this one, make sure you get in contact with me, okay? It's not that hard of an equation overall, but understanding what step goes where can get a little confusing. But it will be important for exam number 3 that you know how to do this. So if you don't have a full understanding of it, please get in touch with me. Okay. Let's go on to question number 2 of our review. Why is increased breathing frequency or hyperventilation a short-term response to altitude? So the second part of that will be, how does it enhance oxygen transport? So let's divide this right here. Let's draw a little line. And this will divide our answers. Okay, so why is increased breathing frequency a short-term response? Well, what it's going to do is it's going to help to make the air inside your alveoli more similar to the atmospheric pressure. It's kind of like if you want say you put a couple of food coloring drops into a beaker of water. You all know what that looks like, okay? If you are stirring that beaker of water, okay, very slowly as that drop of food coloring is going in, it's going to diffuse, over a course of time. What's going to happen if you drop that same dropper but increase the stirring, increase how quickly you're doing that, guess what's going to happen? That's going to diffuse more quickly. So when we are breathing more frequently, the diffusion of that oxygen from the atmosphere into our lungs is going to occur more quickly. And therefore, when we talked about that drop that we had in our last lecture from the atmospheric pressure to the alveolar pressure, that drop is going to be less because we're breathing more frequently, okay? So don't get this confused with when you're hyperventilating too much where you're not exchanging that alveolar air. That's when you're, just breathing in your anatomical dead space. We're not in that situation right now. This hyperventilation is barely noticeable. Most people don't notice that they're breathing faster when they move to altitude, but you are breathing 2 to 3 breaths per minute a little bit faster, okay? So what it does, why it's a short-term response, is it brings pp of oxygen in alveoli closer to atmospheric. Partial pressure of oxygen. And remember, the exact opposite of this happens as well. You get closer partial pressure of carbon dioxide in the alveoli as well. What that does is it increases the gradient between the blood and the alveoli for carbon dioxide, and we get excess carbon dioxide movement out of the blood. Remember, we talked about how that has initial impacts on your blood's buffering capacity. However, right here, we're only talking about this as a short-term response because nothing's changing in your body overall, okay? When we talk about our long-term responses, that's going to be some adaptations that we have, changes in the actual number of red blood cells in your body, Okay, so that's our long term. This is just our short term. How does this enhance oxygen transport is the question. Okay, so the way it does this is we have increased O2 partial pressure in alveoli. If we think back to our lecture before this, what do we talk about over and over again? We draw this figure over and over again that has partial pressure of oxygen on the x-axis, and that is our oxygen hemoglobin dissociation curve. Okay, remember, we drew this nice little figure that looks like this. Right on here is PPO2. If we increase our partial pressure in the alveoli, we're going to move this way. That's going to take us from here on the curve to here on the curve. It's not a lot, but what you'll get is increased HbO2 saturation. Okay, so that's how it enhances oxygen transport. Because we're at higher altitude, that partial pressure of oxygen is already going to be reduced. If we bring that partial pressure up just a little bit, it's going to help with our oxygen saturation. Okay, fantastic. Last part of the review. If a person's hemoglobin increases by 5 grams per deciliter following 6 weeks at altitude, why don't they improve their endurance exercise capacity? Okay, this is a tough one because it gets into some of those long-term adaptations that occur with moving to high altitude. Over time, remember, because your brain's been sensing low oxygen saturation for weeks now, the response to that is, hey, we're not moving enough oxygen. We must need more red blood cells. So let's make some more red blood cells. Inside those red blood cells are hemoglobin. So if that hemoglobin goes up, our oxygen carrying capacity goes up. But the one thing that doesn't change is exactly what we were just talking about a minute ago. This guy right here, our oxygen dissociation curve. So even though you have an increase in O2 carrying capacity with acclimation, PPO2 remains low equals inability to saturate hemoglobin. Basically, what we're saying here is yes, our maximal oxygen carrying capacity is going to go up after 6 weeks at altitude, but we cannot use it. The reason we can't use it is because that partial pressure of oxygen is still low because that column of air hanging above our head that's pressing down on that oxygen hasn't changed. So yes, our maximal carrying capacity is up, but our ability to use it hasn't increased. Hopefully, we will get back to about what we were at low altitude. Okay, so that's our review. Now let's move on to altitude training. I love this part. I hope you guys really enjoyed the article by Levine, classic 1997 article, kind of one of the first live high, train low articles that was out there that showed for a fact that you can do this. Okay, so we're just going to draw a little figure here that looks at time on our x-axis, and then we're going to look at performance as a percentage of 100%. Okay, and we'll put our 100 right here. Let's use a little different color to make it stick out. Here's our red, 100%. Okay, and each one of these little blocks is like, let's say it's a week. So for example, I think in this study they have a baseline period of about 3 weeks, and this is at sea level. They take all the athletes and they want to make sure that they're at the same level. So what they do is they bring them in there and they train them all for 3 weeks, and they see like a teeny tiny little improvement in performance over that 3 weeks. But the benefit there is they just know they've been giving all the athletes the same type of training, and therefore we know we're starting out on the even level. Because one thing that happens a lot of times with these training studies, if we started it for example, we're going to move I think it was 6 weeks there to 7,500 feet. If we just started this study right here and started with a standardized training protocol, we don't know how much of the improvements that we're seeing at that point after this line right here are due to the intervention being, okay, now these guys are on a similar training program, or is it due to the fact that we moved them to high altitude? Okay, so the reason that we do that, like kind of work in period or that baseline period, is just to make sure that we know most of these people are used to this training program and we're ready to go. And we can now compare based on the individual independent variable, which is movement to altitude. Okay, so let's move on. So now these individuals, these runners, move to high altitude, and it was really interesting. This is specifically, we're talking about the group that stayed at high altitude. Okay, so they lived high and trained high. This is not live high, train low. This is live high, train high. So this is a person coming from San Diego to Laramie from sea level to about 7,500 feet. And what's going to happen? As soon as they get here to high altitude, okay, you're going to get a rapid decrease. Oop, not erase. Sorry. Rapid decrease. And these are just arbitrary units here on our y-axis, but we're going to see that giant kind of movement. And then over the course of, it depends on which kind of notebook you read here for how long this is going to take. But what we're going to say is by about 6 weeks or so, your performance should be back to about 100%. That's not necessarily the case with everybody, and we're going to go over some of that in a little bit. But I want to put kind of like an error bar in there. Whoop, not that way. Some people will not be back to performance. An example I give here is, okay, at the end of this point right here, let's say you could run a 21-minute 5K. After about 6 weeks of being about 7,500 feet, if you maintain your training schedule, you should be able to run just about a 21-minute 5K at high altitude as well. Okay? Now, what we're going to do here is with these 2 weeks at the end, we're going to move you back to sea level. And what has happened here? Well, in this initial period right here, this is where you have your acute response. In that acute response, remember, we're hyperventilating more, we're losing plasma volume. All of these things, all of these changes that are happening are not going to be conducive to athletic performance. So as we see in that period there, that first 2 to 3 weeks, we have some very, tangible decreases in performance. But then, in these periods here, we're going to have our adaptation. And within that adaptation, we have increased number of red blood cells. Okay, that allows us to basically get back to where we were now that we're high altitude. But remember what we just said at the end of our review. We have increased our maximal oxygen carrying capacity. But we can't use it necessarily because we're at a low partial pressure of oxygen. So what happens if you increase your oxygen carrying capacity and then move back to sea level? Well, what we see here is a slight potential increase in exercise capacity. This is short-lived. So, what we're saying here is that if you increase your red blood cells or your hemoglobin mass by being at high altitude and then move back to low altitude, you have a small window there where you might be able to use that red blood cell mass to carry more oxygen in your blood to your muscles, where the partial pressure, once again, is elevated. So now we have all of these extra red blood cells. We can saturate them because the partial pressure of oxygen is there to push all those red oxygen molecules out of the alveoli into the blood and onto the hemoglobin. So now we can saturate them, and then we can get that oxygen to the working muscles. So if the limiting factor of your VO2 max was oxygen transport, this is going to help. Is it going to help you get more mitochondria? Not necessarily. So if the limiting factor of your VO2 max at high altitude was your number of mitochondria or mitochondrial density, this is not really going to help with that too much. So this gets into our next point. What adaptations do we see with this? Okay. And if we want to go over this, we have some general timelines, and these timelines are not necessarily related to athletic performance. They're related to some other more basic metrics. So although in my figure above I show 6 weeks to get back to normal for exercise performance, the classical definition and what you'll find in your book is that it takes about 2 weeks to acclimate to 7,500 feet. Okay? And then for every 2,000 feet above is an extra week. So if we wanted to go to 9,500 feet, that would take us 3 weeks. 2 weeks to get used to the 7,500, and then 1 more week to get used to that 9,000 feet. Okay, so if we want, or 9,500. So if we wanted to go to 9,500, it would take us about 3 weeks to get used to that, right? And that means just getting back to your normal kind of resting capabilities, not exercise necessarily. But the things that happen as far as adaptations, well, we are going to increase our O2 carrying capacity. Why does that happen? We just talked about it. You're getting more red blood cells, more hemoglobin subunits, more oxygen carrying capacity. You're going to increase your arterial hemoglobin saturation. You're also going to increase your exercise O2 consumption. Because there's a little bit of a scarcity of oxygen in the beginning stages of your movement to altitude, your muscles get a little bit better at extracting that oxygen off. So that's part of it as well. You're also going to increase your power output at submax intensity. So this is important when we think about, long distance endurance sports like cycling or running. Your power output is directly related to your ability to, do well in an event. Okay. So if we're going to increase our power output, let's say you could maintain a power output, a wattage on the bike of 200 watts for 1 hour. Now, obviously, that's your submaximal intensity because you can maintain it for an hour. However, if you move to altitude, after about 2 to 3 weeks, you might be able to maintain 210 watts for an hour. Okay, that's submaximal intensity. Your power output is going to be increased. However, your maximal intensity, if you're coming down to a sprint at the end of a bicycle race, it might not be any difference. So, how does this type of training, movement to altitude, and getting those performance improvements from those physiological changes affect your performance at altitude? Well, absolutely. And what do I mean by that? Well, if you are going to be competing at high altitude, remember we talked about Mexico City in the last lecture about that marathon that was there, that all the times were slower. If we took one person and gave them kind of 2 trials at it, okay? So, or 2 people who are identical twins. Both of you, before both of those people, let's say here's Dr. J and then my evil twin. We're going to look at 2 time points, okay? I and my evil twin have a marathon PR of 3 hours and 14 minutes. And that's true. That's my actual marathon PR, Philadelphia Marathon, okay? And what's going to happen is I, non-evil Dr. J, is going to move to Mexico City for 6 weeks before the Mexico City Marathon. Evil Dr. J is like, no way, I got stuff to do back here in Laramie. I'm going to hang out. I don't want to be bothered with going to Mexico City too much beforehand. And no acclimation. What's going to happen? Am I going to run slower in Mexico City? Probably. Okay. So I might run a 3:18 in Mexico City. But guess what's going to happen to the person who didn't acclimate beforehand? 3:25, something around there. A real big decrement in performance. So when it comes to saying, does movement to altitude before competition at altitude improve performance? Yes, even if that means your time is slower. All right, it's your relative performance. So you're going to do better in relation to people who don't do any sort of that acclimation. Now, the question comes up, and kind of the hard part is, what about your performance back at sea level? And we just drew in our figure above, right here. We drew this nice thing. Look at that. Oh my gosh, if I live in Laramie for 6 weeks and I have a big race back on sea level, I'm going to go race the Carlsberg Marathon, which is a traditionally fast course on the coast of California, really super flat course right along the ocean, beautiful course. That's going to be my best case scenario for doing that. Well, the problem is that you have a range of improvements. And even if you look into that article, you'll see this. Some people, after being at high altitude, they went back to low altitude, they got worse. How does that even make sense? You have a range of improvements. And this goes from about -5%, this range of improvements includes getting worse, to about plus 15%. So some people get a real big boost from doing this type of training. Other people actually end up doing worse. And the rationale for doing worse is when that person moved to high altitude, they probably didn't get back into this range of where they were able to exercise at the same intensity they were prior. So if they weren't able to exercise at the same intensity they were exercising at before they moved to altitude, well, now they're going to be worse. Because let's say, the example I give, even though it's not an endurance sport, is like bench pressing. Okay, before you move to high altitude, you could bench press 100 pounds, just like me. I can bench press 100 pounds 10 times. That's it. And when I move to altitude, I expect that ability to go down. So, okay, now I can only bench press 70 pounds 10 times. But over the course, I get a little bit better. Okay, now I can do 75 pounds 10 times. Okay, now I can do 80 pounds. Some people are able to get back to their 100 pounds. Other people are never able to get back to that because of their ability to exercise at high altitude. And they can't get back to 100 pounds. So all they're able to do, the most they're able to do when they're at high altitude, is bench press with 90 pounds. Still 10 pounds short of what I used to be able to do. Well, now I'm going to move back down to low altitude. Do you think I'm going to be able to bench press 100, 110 pounds now? No, because I was never able to reach that training intensity that I was at. There's a lot more involved with endurance exercise performance than just carrying oxygen. That's a big part of it, but there are other biomechanical factors associated with it as well. So you have to keep those, and neurological factors as well. So we have our range of improvements from about 5 to 15%. And we will call these non-responders to responders. And you have this in a number of different type of interventions overall. But if we were looking at the overall improvement back at low altitude, overall equals about 1%. So on average, if we took 100 people and did the same protocol with them, if we looked at everybody's race time, let's say 5K time, before they left and within that 7 window after they get back from training at high altitude, if you looked at the average improvement, it would be about 1% faster. For some athletes, Olympic athletes, for example, that's the difference between first place and not even coming on the podium. 1%, especially in something like a marathon, is a big chunk of time. Even in a 5K, 1% improvement is a big win when these people have been training for years and years and years, are pretty much ceilinged out as far as their athletic ability can go. If you can say, hey, we can get you another 1% of performance, they're going to take that, especially with the chance of moving to 15%. So this is with live high, train low, specifically. And let's get into that. Right here, we talked about only being at high altitude the whole time. What if we brought a person to high altitude and then had their training sessions back at low altitude? Let's take a little break. Let's see if I can find a little bit of white space. I can. Right here. Okay, so we're talking about live high, train low, and this is what the research article that you read gets into. Before, we've only talked about living high and training high and how that benefit gets back there. But if you live high, over that 21 days, you increase your red blood cells. Okay? The downside of training high is that you can't exercise at a high intensity. Remember, your ability to transport oxygen is going to be compromised. But if we keep going down to low altitude for your training sessions, you can maintain your training intensity at the beginning stages of that. And let's say you stay at this high altitude for 6 weeks, 8 weeks, 3 months you stay there. And for each of those workouts, well, eventually you can increase your training intensity because you have increased your ability to transport oxygen based on those increased red blood cells. Your hematocrit has gone up. So let's say a great example for a 5K runner. Let's say there's somebody running the 5,000 meters in the Olympics. A workout they would typically do to improve their ability at that top end speed would be like 400-meter repeats. So one lap around the track with minimal amounts of rest. And they would try and do, 10, 12, 20 of those depending. And that's improving their ability to work in that lactate threshold area. They're exercising really, really hard for those 400 meters, okay? So before they move to altitude, let's say that their best ability to maintain the same time for like 10, 400 meters was they could do that in, let's say 54 seconds. For each one, they could run 100 or 400 meters in 54 seconds, take a short break, and then do it again. And they could do that 10 times and know that each one of those would be exactly 54 seconds. Well, when they first moved to high altitude, we know that time is going to go down a little bit. But if they're there for a long time and they keep going down to low altitude where that partial pressure is once again high and they have expanded oxygen carrying capacity, well, maybe I can now run these not at 54, but 52. So what we're getting into here is the training effect, not just the ability to transport more oxygen. Because remember, we talked about VO2 max, all right? If before all you're doing is going back for that one race. Well, now we're going back time after time and increasing the training stimulus. What we're doing is we're having you work harder during your training sessions. If you live high, train low, that will potentially change your musculature so that you can actually run faster. So that's what live high, train low is. And when we talk about those adaptations down here, this is live high, train low. That's not just with moving to high altitude and just hanging out there, okay? So I had a great question come in. Somebody sent me an email from the class and said, hey, we're talking about oxygen here. I've heard about anemia before, and I've heard a lot about iron supplementation, and that's important for people who are exercising at high altitude. And they said, why is this? What is the mechanism that's associated with this? And I don't normally include this because this is a little bit outside of the scope of what we normally talk about, but I wanted to include it here because I thought it was just such a great question and really applicable to what we're doing. Okay, so let's just briefly cover iron's role in oxygen transport, relation to nutrition, and how that applies to altitude acclimation. So let's start here. We've talked about our red blood cell before. Pretty easy. We've also talked about within that red blood cell, there are 4 hemoglobin subunits. Look at this. Dun, 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 dun. But then the cool thing is within each of those hemoglobin subunits, right here, you have your iron atom. There it is. That iron atom makes up that hemoglobin subunit. If you don't have that iron atom, you cannot make that hemoglobin subunit. So when we take in iron with our diet, it is then included in these hemoglobin subunits. All right? Remember, before we talked about this. This is why I picked the second picture, is because we have our deoxygenated form on the left and our oxygenated form on the right. And what you can tell about the difference of these is the conformational shift that occurs after it is oxygenated. It's a little bit difficult to tell, but the example I use, here's this guy who's going this way right here. Oh, well, now it's going in a different direction once it's oxygenated. That is that conformational shift that allows that process of cooperativity to occur. So now it's easier for that oxygen molecule to bind to the second hemoglobin subunit on there. And once again, here you go. Here's our heme. Here's our iron. Here's our heme. Here's our iron. So we have to have that iron to make our hemoglobin. So a classic disease that we see associated with this is anemia. And all anemia means is you're lacking enough healthy red blood cells to carry adequate oxygen to your body's tissues. And there are a bunch of different types of anemia. So if you are diagnosed with anemia or you know someone who's been diagnosed, it's not necessarily true that just giving them a little bit of iron supplementation is going to help with that. But it can help because just like we said before, if you're not taking in enough iron in your diet, well, then you don't have the building blocks. Let's say you move to high altitude and you get that stimulus to make more red blood cells. Your erythropoietin goes up, okay? Your body's saying, we're not carrying enough oxygen. Let's make some more of those carriers. Here we go. All right. But then you dig into what's known as your iron pool. In your body, you have basically, just iron that's hanging out, ready to be built into hemoglobin subunits. If that iron pool is very low, because your dietary intake is very low, well then, no matter how much stimulus there is, there's not going to be the ability to make any more of it. Okay? So what happens when we look at iron supplementation in athletes, specifically those moving to high altitude? Okay. So this is a great study. Here we go. Pre-altitude serum ferritin levels and daily oral iron supplement dose mediate iron parameter and hemoglobin mass responses to altitude exposure. Woo! Basically, what they did in this study was they took athletes who were going to be moving to an area of high altitude and they gave them 3 different doses of iron. 0, let's move on to our figure right here, 105 milligrams a day and 210 milligrams a day. And what they looked at is, first in our table right here, the most important thing, hemoglobin mass. Did our amount of hemoglobin go up? And what we see here is that we have, these are our confidence intervals. This is our average right here, 1.1, 3.3, and 4. So hemoglobin mass went up with everybody, but look at this. In our 0 group, we had some people go down. Responders, non-responders. But if you gave them some iron supplements, you might see that, oh, look, our ability to get to that top end goes up. And the reason that top end goes up is because you have more of those building blocks sitting right there. And if you look at the incorporation, so what they did is they probably labeled the iron that they were giving them as a supplement with something that they could actually be able to determine with an assay, so they could measure how much of each one of those hemoglobin subunits was made up of that supplemented iron. Well, they looked in 2 spots, okay? SII, the red cell compartment within the red cell itself, and HII, iron storage. SII is the storage of iron, okay? So that's just in the blood plasma, and the red cell compartment, HII, that's just going to be within the red blood cell itself. And what they say, if you had no dosage right here, most of your people had a negative amount of incorporation, okay? So they had a lower amount of iron. If you looked at people who got 105, well, you saw some who were negative and some who were on the positive side. If you looked at the amount of storage, it went down a little bit. But if you looked at the incorporation, it went up. Well, if you looked at the people who got 210, both their storage and their incorporation went up. And that's going to hopefully result in an ability to exercise aerobically at high altitude and within that 7-day window a little bit better. So I hope that answers some questions right there about iron supplementation and movement to altitude. Remember, the reason why iron is important for altitude is because it's included within that hemoglobin subunit. And if you don't have enough iron in your diet, you don't have the building blocks to make more hemoglobin when that stimulus comes around, okay? So I thought about moving on to breathing regulation today, but this is a completely new topic. I added to this lecture by adding in the part about iron, so I'm going to end it right there today. Remember, you have an extra day of timeline to complete your homework. If you have any other questions about that, please get in touch with me. Oh, the last part that I'm going to include here, okay, we had an elimination of, I think, 4 or 5 of the extra credit lectures. So what we're going to do is I want to open this up. I miss the interactions I get to have with everybody in the class during class for asking questions, being able to gauge how what kind of comprehension people have. So I want to bring that back, but I also want to give everybody the ability to recoup all of those extra credit points that you weren't able to get. So if you have a question in response to any of our lectures, write them down in an email to me, okay? You have the ability to gain 3 question bonus points, 1.5 points for each one. So send me an email with a question that's directly related to one of our lectures. You could send me a question about adaptations to altitude training, something along those lines. Hey, this didn't make sense to me. This is going to serve 2 purposes. First, it's going to get me to answer some of the questions that you guys have from lecture. Second, it's going to give you the ability to gain back some of those bonus points that you weren't able to get because our seminars were canceled for this semester. So, like I said, you have the maximum ability of getting 3 of those. I'm going to double check the number of lectures that we missed. It might have been a couple more. I will equate the number of questions that you can submit, and now it has to be for separate lectures. Don't just submit 5 questions and think you're going to get 5 bonus points. 5 for separate lectures, and that will be added to your final grade, just like the ones from before the seminar series. The one caveat that I have with this, I have to get these questions within 24 hours of posting the lecture. The reason for that is because I want to make sure that I include my response to those questions with the next lecture. So make sure that you do that. All right, guys, I'll see you on Wednesday.